Is the car a blessing or a curse? We tend to thank technology for giving us the benefits of mobility, but at the same time blame it for air pollution and other environmental damage. We'll see that materials science and engineering can't cure the problems of the modern world, but they can lessen some of the harm done by our use of technology. The basic design of cars hasn't changed much in decades, and you may think they don't look very different from how they did, say, 20 years ago. But in fact, there have been some quite profound changes in the materials and the range of materials that are used in cars that aren't quite so obvious from the outside. Something over 10% of the weight of this car is made up of plastics materials, and that figure is likely to increase as manufacturers start to replace the steel in body panels more widely with plastics and plastics composites. But that's part of a general move to lower density materials. Lower density materials means lighter cars, and lighter cars need smaller engines. Smaller engines, in turn, use less fuel. Now that's good for the car owner, naturally, but it's also good for the environment because it means less air pollution for the same distance driven. So there are moves to reduce the amount of exhaust gases produced. But what about the composition of those gases? One recent development that's unlikely to have escaped your attention is here at the MOT testing station. Exhaust gas testing is now an essential part of the annual vehicle test. Early concerns over photochemical smog in California led to more general interest in air quality and health. Car emissions were known to be a major contributor to air pollution, and 3 particular components of the exhaust gases were identified as the major culprits. Of the 3, carbon monoxide is arguably most dangerous. Its molecules consist of 1 atom of carbon combined with 1 of oxygen. It's highly reactive, and that makes it toxic. Carbon monoxide in the air we breathe combines with hemoglobin in the blood to block the absorption of oxygen. NOx is the shorthand for various oxides of nitrogen, from nitrous oxide to nitrogen dioxide. They combine with oxygen and water in the atmosphere to produce nitric acid, a contributor to acid rain. NO2 itself is toxic and leads to throat and eye irritation. In sunlight it produces ozone, the major constituent of photochemical smog, by reacting with the 3rd group, the hydrocarbons. That's unburnt fuel that passes through the engine. Petrol contains hydrocarbons having between 5 and 8 carbon atoms. Diesel fuel is a mixture of hydrocarbons with between 13 and 25 carbon atoms. Apart from their role in the production of photochemical smog, hydrocarbons are very powerful greenhouse gases. There are other components to exhaust gases which aren't currently part of the test. One of those is sulfur dioxide, which comes from sulfur in the fuel, but in a sense that needn't be an issue because you can take the sulfur out of the fuel before you burn it. But something that causes more concern are what is known as particulates, and that's principally the smoke that you get from diesel engines. There's a lot of debate about how to deal with smoke and soot, but as yet there are no universal solutions. So how do these byproducts come to be generated in the first place? The basic chemistry of combustion inside the engine is the reaction between the hydrocarbons in the fuel and oxygen, oxidation. In a chemically perfect engine, the only products would be carbon dioxide and water. But there are several problems in a real engine where the combustion happens very quickly and the temperatures are very high, around 1600 degrees Celsius. And of course it's not pure oxygen that's mixed with the fuel, it's air containing 80% nitrogen. If you want to convert all the fuel into carbon dioxide and water, you need just the right amount of oxygen. That's what's known as the stoichiometry of the reaction. The trouble is, you can't help using up some of the oxygen in converting some of the nitrogen in the air into nitrogen oxides, and that leaves some of the fuel unburnt or only partially reacted. These graphs show the possibilities for remedial action. Levels of the 3 major pollutants are shown plotted against the air-fuel ratio. One option is to increase the air operating to the right of the curves. That would reduce the CO and HC, but at the expense of increasing NOx. At the optimum air-fuel ratio, there's still a significant amount of all three pollutants in the exhaust. To get rid of those requires a different approach, and this has now been adopted throughout the USA and Europe. The trick is to convert the NOx back to nitrogen, freeing the oxygen to react with the unburnt hydrocarbons and the carbon monoxide, converting them to carbon dioxide and water. It's called a three-way catalyst, the catalyst being a substance that promotes the various reactions but doesn't itself change chemically in the process. It's long been known that platinum, a rare and expensive metal, can act as a catalyst to oxidation reactions. This powder contains platinum particles. The machine they're being tipped into is known as a TAP reactor. TAP stands for Temporal Analysis of Products. That means it allows the concentrations of both the reactants and the products of a reaction to be measured over time. The progress of reactions in the gas phase can be followed in such an instrument. A small quantity of catalyst is placed under vacuum in the chamber of the instrument, and a fine stream of the reacting gases is made to flow across it. The test can gauge the effectiveness of particular catalysts or combinations of catalysts by providing a measure of how long the reacting gas needs to be in contact with the catalyst before breaking down. The computer can present the data as two traces, which represent the concentrations of first the reacting gas entering the test cell, and then the products leaving the cell. The separation between them, around 10 milliseconds, tells you how long the conversion from one to the other takes. A real exhaust system is more accurately modelled in this test, where a mixture of gases similar to those found in a car exhaust flows over a sample of catalyst. The catalyst itself is in a reaction vessel at the centre of the coil of tubing. The blue cylinder is an electric furnace. As it steps towards the reaction chamber, the temperature is raised in controlled stages. As the temperature rises, the compositions of the input and output streams are analysed, but this time the difference between the two is expressed in terms of a conversion efficiency. The computer screen shows how the conversion efficiency for each gas varies with temperature, and you can see that below a certain temperature the efficiency is 0. This is the light-off temperature. Below this temperature, about 300 degrees Celsius, the catalytic converter performs no useful function, but above the temperature it works extremely well. This is the basis of the engineering solution. It's a ceramic block with channels for the exhaust to run straight through from front to back. It contains just a few grams of the combination of platinum, rhodium and cerium that lab tests confirmed would be the ideal mixture. But the gases in a car exhaust can flow at hundreds of litres a second. How could a few grams of precious metal be distributed so that all the exhaust gas would remain in the converter long enough to be treated? To answer that question, we need to use a number of different imaging techniques to see inside its construction. The structure of the catalyst block is best shown using the scanning electron microscope. Samples are first cut from the ceramic honeycomb and embedded in polymer resin before being polished to give an extremely flat cross-section. A metal coating has to be applied to stop the sample developing an electrostatic charge inside the machine. Once inside the evacuated chamber of the instrument, a beam of electrons is scanned across the surface of the sample, and these displace some electrons from the outer orbitals of atoms in the sample. These so-called secondary electrons are collected and focused to create an image of the surface. The use of a beam of electrons rather than light allows a resolution down to about 1/10 of a micrometer, but here we are only seeing a magnification of a few hundred times. As the magnification is increased, you can see that the corners of the channels are rounded. Quite a thick coating known as a wash coat has been applied to the ceramic core. This too is a ceramic material, mainly aluminium oxide and containing some barium oxide. What you see here is a corner of one of the cells. The important thing about the wash coat is that it's highly porous. The pores are tiny, mind you, so you can't make them out at this magnification. but they in effect form a ceramic sponge and increase the surface area by something like 7,000 times. That's the equivalent of the area of 2 football pitches inside each catalyst block. An adaptation of the principle of the scanning electron microscope can determine chemical composition by measuring the energies of X-rays emitted from the sample. The technique is known as electron microprobe analysis. The image produced is coloured by the computer to show the distribution of the various elements present in the sample, white being the highest concentration. Here you can see the distribution of the aluminium and the barium of the wash coat. The active catalytic ingredients, platinum, rhodium and cerium, are shown as having much lower concentrations. You can see how the concentration of platinum is much higher at the surface of the wash coat than in its bulk. That's deliberately so to increase the total catalytic action. But microprobe analysis can still only give you a rough idea of the whereabouts of something like the platinum, which is intended to be distributed on close to an atomic scale. This thin sample is what's needed for an instrument that can examine fine atomic detail of distribution. The thin film is nearly transparent to electrons. The instrument is the transmission electron microscope, which bombards a sample of material with an electron beam and picks up and images the electrons that pass through the sample. The image is produced on a green fluorescent screen, which itself is viewed through an optical microscope. The black spot in the middle of the screen is actually a grain of platinum. The manufacturer is aiming to spread the platinum as thinly as possible through the wash coat, and the TEM allows us to see how well the process is performing. The sample irradiated by electrons emits X-rays, and these too can give an indication of the elements present under the beam. It's shown as an energy spectrum on the VDU. The intensity of radiation at a frequency characteristic of the element gives a measure of its amount. As you would expect, the peak for aluminium is greater than that for platinum. To get a precise quantitative analysis of the elements present in the ceramic, albeit in the top few nanometers, we need the fourth analytical technique, X-ray photoelectron spectroscopy, or XPS. The sample is now a longitudinal section through the catalyst block. It will be bombarded with X-rays over about a square millimeter of its area. Here it is inside the machine. The red spot is just a positioning laser. The X-rays knock electrons out of the atoms in just the surface layer, and these electrons have energies characteristic of the atoms from which they've come, so they can be identified with particular elements. But what's more, it's possible to tell the oxidation state of the element, and so you can tell if, say, a metal is in its pure state or combined with oxygen. The machine's output is a spectrum of energy. Peaks correspond to the characteristic energies of the electrons emitted. This graph shows just how little platinum and rhodium there are in the catalyst block. Their peaks are almost invisible against the background noise in the signal. If we zoom in, you can see just how small they are. Even having a perfect design of catalyst at the atomic level isn't enough, though. This graph shows the effectiveness of the three-way converter at various air-fuel ratios in the engine. There's only a narrow band in which the catalyst works on all three pollutants. To keep an engine working in this band, to this air-fuel ratio, requires further engineering changes to the engine as a whole.
You have to have an engine management system that maintains the air-fuel ratio as close to 14.5 to 1 as possible. That number is sometimes called lambda is 1 equals 1. Lambda is the equivalence ratio. And it is done by mainly by an oxygen sensor in the exhaust pipe, sometimes known as a lambda sensor. And that feeds back into the engine management system, which is an electronic control system, which then controls the fueling from the electronic injectors and probably the spark ignition as well. So The technology means that, for example, carburetors are no longer viable for use with a three-way catalyst.
So it's not enough just to design an effective treatment process for the exhaust gases. The engine has to work as a system. That's where the engineering comes in. And there's a lot of engineering in the design of the exhaust system alone. To make a working catalytic exhaust system, the catalyst brick needs to be robust enough to survive both the assembly process and its working environment. It has to be firmly fixed inside the exhaust system, and the whole assembly has to be gas-tight, so that all the exhaust gases pass through the catalyst. Excess heat at this stage could be disastrous. Any damage to the ceramic or its packing would allow it to vibrate inside the exhaust, and that could result in it breaking up. So the two halves of the shell are tacked in place by spot welding, where an electric current is passed through the joint between the two electrodes. Then the whole seam is welded and sealed at the same time, using a similar but continuous process known as resistance seam welding. The two rollers act as electrodes, and the high electrical resistance at the joint generates enough heat to melt and fuse the metal. But the heat is confined to the joint between the two sheets of metal. Finally, the complete canister can be welded into a length of pipe to mate with the exhaust system. One of the greatest challenges for the engineer has been to design a long-lived catalytic exhaust system. Regulations in force in the United States require catalysts to go on working for 50,000 miles, and that's due to be increased to 100,000 miles very shortly. And despite containing only a couple of grams of precious metals, the brick itself is sufficiently expensive that you don't want to have to throw it away simply because the exhaust pipe has corroded. So stainless steel exhaust systems are now very much the rule, and rusty exhausts could soon be a thing of the past. But there are still engineering problems. Remember, catalytic converters don't function at all below temperatures of around 300 degrees Celsius, the light-off temperature. It's only in engine test cells like these that engines run continuously. As any driver on a winter morning knows, to get the engine started, you need fuel enrichment, or a choke on carburetor engines. And with a cold catalyst, the cold start plays havoc with the emission levels. Test cells like these enable engineers to put figures to this problem.
Anything up to 70% of the emissions over a 20-minute cycle will appear in the first 3 or 4 minutes. So the cold start is the Achilles heel of the current catalyst, three-way catalyst system.
The most realistic figures come from tests on engines in cars driven on the road. In the lab, it's done on a rolling road. This technique is also used to obtain approval of new engine designs. For those tests, the car is driven according to a strictly laid down schedule of speeds. The test driver must keep to the speed profile shown on the computer screen, which also details gear changes. Throughout the test period, the exhaust emissions are collected and analysed. This can be done instantaneously to give a complete rundown throughout the drive. Carbon monoxide, hydrocarbons and NOx are measured, as well as fuel and air intake. Part of the official rating includes average readings over longer periods of the test. For this, samples of exhaust are also collected in these gas bags, and the contents analysed after the drive has finished. The results of using the three-way catalytic converter are impressive. Compared to 20 years ago, emissions of CO from a typical car have fallen by over 90%. As a proportion of total emissions from the car, the pollutant levels are minute, less than 0.25% by mass, but the standards are tightening. The 1995 official limit for CO is 2.2 grams per kilometre, with future targets lower still. How will engine designers cope with this challenge?
The emphasis has to be on the cold start section, because that's where the predominance of hydrocarbon emissions comes from. There are various ways of doing that, but effectively we're trying to counteract the effect of fuel enrichment, and we're trying to come up with a catalyst that is up to operating temperature very, very quickly. For example, by electrically heating it. By having an electrically heated catalyst that is pre-warmed, it's already up to temperature when you first start fueling the engine. The snag with an electrically heated catalyst, the ones that are being worked on at the moment take anything up to 400 amps. So it doesn't take many cold starts to have flattened your battery completely. There are other ways of doing it, inserting fuel, squirting fuel into the exhaust system with excess air and burning the fuel to pre-ignite the catalyst. Obviously it doesn't do anything for the fuel economy. Putting the catalyst as close as possible to the exhaust ports, instead of having it some way down the exhaust pipe where heat will be lost from the exhaust pipe. If you have a close coupled catalyst, you can take advantage of the hottest gas as it comes out of the engine. The snag there is getting a decent flow across the catalyst because you haven't got much room to mix the flow. And the other problem is that once the engine is fully up to temperature, you're in danger of overheating the catalyst. So there are a number of technological solutions, all of which need considerable development.
As you may have spotted, this is one of the ways of getting around some of the problems of exhaust emissions. It's a diesel car. Diesel engines operate at much higher air-to-fuel ratios than spark ignition engines, and that means that they intrinsically produce smaller quantities of carbon monoxide and hydrocarbons, and they use less fuel into the bargain. But no matter how much trouble we take over cleaning up exhaust gases, we're still left with the problem that vehicle use currently accounts for almost 25% of carbon dioxide emissions in the UK. And carbon dioxide is itself one of the prime suspects in the debate over the greenhouse effect.
I think the problem is beginning to move away from the field of engineering into the political arena, the green arena, if you like. The big problem, I believe, is the sheer numbers of cars. You could halve the emissions from cars just by halving the number of cars on the road. Halving the emissions from a car by doing an engineering solution is very much more complicated.
When I started